This is part 2 of our lectures on computations in geometric optics.
In part 1, we discussed basic principles of drawing ray diagrams and using ray approximation. Now let's talk about the second method based on the mirror equation, or as it is also called, the thin lens equation. Both methods are needed for solving the problems in your homework assignments. The mirror equation that we will now discuss follows from the existence of a special point near the mirror, called the focal point. The key property of the focal point is that any incoming ray that is parallel to the central axis of the mirror before the reflection will pass through the focal point after the reflection. On the other hand, if the incident ray passes through the focal point before the reflection, it will be parallel to the central axis after the reflection. The incident parallel rays are reflected by the mirror so that they become outgoing focal rays, while the focal rays are reflected as parallel rays. If we now follow these rays to find the position of the image they form, we observe something interesting. In the figure that you see, the image of the tip of the arrow is formed at the point where the parallel and focal rays cross after reflection. We can denote the height AB of the object as h and the distance AO from the object to the center of the mirror as p. Similarly, we can denote the height AB prime B prime of the image by h prime and the distance A prime O from the mirror to the image as q. Take a closer look at the geometric pattern formed by the rays. You may notice that they form several pairs of similar triangles. Two such triangles, ABF and COF, are shown in green. They have equal angles at the corner point F. The sides of these triangles satisfy similarity ratios, such as length AB divided by length CO prime is equal to length AF divided by FO. If we express this length in our variables, we find the relation h over h prime is equal to p minus f divided by f. There is another pair of similar triangles, A prime B prime F and COF. Using the similarity relations, we find that the ratio h over h prime is also equal to f divided by q minus f. Altogether, we find that h over h prime can be written either as p minus f divided by f or as f divided by q minus f. Thus, we have a relation between p, q, and f. We can simplify this relation a bit by multiplying both sides by f times q minus f. Expanding the left-hand side and cancelling the common term f squared, and finally dividing by pqf. We get the final result that 1 over p plus 1 over q is equal to 1 over f. This is the so-called mirror equation. It turns out that it also holds for other types of mirrors and lenses. The mirror equation takes the simple form shown here. It depends on the object distance p, which is the distance from the object to the optical element, such as the mirror or lens, the image distance q, which is the distance from the image to the optical element. Sometimes the distance q is denoted by I, for example in your textbook by Halliday, Resnick, and Walker. Finally, the third parameter in the mirror equation is called f. It is the focal length of the mirror or lens. It is a hardwired parameter of the optical element. Now, the equation, as you see, is quite simple. It tells you that 1 over p plus 1 over q is equal to 1 over f. The subtlety arises because all three distances can be positive or negative depending on the type of the optical element and the relative position of the object and the image with respect to the optical element. For example, let us discuss the sign of the image distance q. It can be positive or negative depending on the type of the image. From your textbook, you know that images can be magnified, reduced, or of the same size as the object. In other words, the apparent size of the image does not have to be the same as the size of the object. Images can be upright or inverted, means their orientation can be reversed compared to the orientation of the object. Finally, the images can be real or virtual. A real image is formed when light ray goes through the point where image is located. So since light goes through this point, the real images can be displayed on screens. As if you put the screen in the position of the real image, there is a light going through this point which can form this image on the screen. On the other hand, a virtual image is formed at a point which light rays cannot reach. So light rays only appear to diverge from the point where the virtual image is located. However, the light is not at that point in reality. For example, when you look at the mirror, you see your image behind the mirror. There is no light behind the mirror. Light only appears to diverge from the point behind the mirror. In the next few slides, I summarize sign conventions for the mirrors as well as thin lenses. The equation that we use with all these optical devices is the same. However, sign conventions will generally change. In the case of the mirrors, we have to distinguish between the front or real side of the mirror, where all truly existing objects are located, and the back or virtual side, where only images are located. Now, of course, when we have one mirror, any object will be in front of the mirror. An image will be behind the mirror, unless the mirror is curved. And in some rare situations, the image will be formed in front of the mirror, so the image will be real. For most cases, the image in the mirror is virtual. However, sometimes we will have a combination of mirrors where the image in the first mirror serves as the object for the second mirror. So sometimes we will find a situation when the object is located on the virtual side. It only happens when we have several mirrors. So then, depending on the relative position of the object and images in the mirrors, we will choose appropriate signs for P and Q. The signs will be summarized in the table shown on the next slide. Here's a table that shows the sign conventions for the mirrors of different kinds, as well as type of images in mirrors. So you can choose the sign, which can be plus or minus for PQ, as well as F. Table also shows whether image is upright or inverted. Similar sign conventions apply for thin lenses. In this case, the front side of the thin lens is the side of the incident light. The light is refracted into the back side of the lens, and in this case, of course, the light is not reflected, it goes through the lens. So we have the incident light and the refracted light. This table shows the sign conventions for the converging and diverging lengths. In this case, converging lenses will have positive focal length, while diverging lenses will have a negative focal length. Depending on whether the object is in front of the lens or in the back of the lens, it will have a positive or negative distance p. Again, there can be a situation when the object created by one lens is in the back of the second lens. Object of the second lens is a virtual object. We will use a negative sign with the distance p. Similarly, depending on the type of the lens, the image can be in the back of the lens where the refracted light goes, so it will be a real image. Sometimes, for diverging lens, it will appear in the front of the lens. So in this case, it will be a virtual image. The image can be upright or inverted, depending on the type of the lens. And finally, whenever you have several lenses, as I just said, you will have to pay attention whether the images and objects are in front of the lens or the back of each subsequent lens. So then you will have to choose the right signs.